Okay, we're going to be talking about expanding binomials, the binomial theorem, and Pascal's triangle. So first of all, let's expand a few binomials and kind of see what we're talking about here. And this is kind of probably what they did historically and how they came up with these different theorems by looking and seeing patterns and then trying to justify those with theorems. So first of all, if we take x plus y squared, this just means x plus y times x plus y. And we use kind of an application of the distributive property twice, which we sometimes call the FOIL process. So we have first term x times x is x squared, x times y is xy, and we'll write these in alphabetical order so we can see where the like terms occur a little bit easier. And then we'll multiply everything in this binomial by the second term. So y times x is again xy, and then y times y is y squared. And then we see we do have like terms xy and xy, so we can combine those. And we end up with x squared plus 2xy plus y squared. So that's a nice easy expansion. Okay, now let's try the next one, which would be x plus y to the third. Now that's just x plus y times x plus y times x plus y, but we already did the x plus y times x plus y as x plus y squared. So I can kind of piggyback off of this work. And then I can just say x plus y times x plus y squared, which is x plus y times this, x squared plus 2xy plus y squared. And I'll multiply it out. And again, we use a double application of the distributive property. So first of all, multiply every term in this trinomial by x. And since that's x to the first power, I just add 1 to each exponent. So x to the third, 2x squared, y, and y, 1x, y to the second. Okay? Then I'll multiply everything in this trinomial by y, and that's going to be yx squared, but I'll keep it alphabetical, so x squared y, and then 2, and then we'll just multiply by y, so 2xy squared, and then y cubed. And then again, you can see how your like terms line up. We do this vertical process, makes it a little bit easier. We've got x to the third, 1 here, and 2 makes 3 x squared y's. 2 plus 1 makes 2 x y squares. I'm sorry, 3. 2 plus 1 makes 3 x squared x y squares, and then y to the third. So here we go. All right, let's try another one. X to the fourth. And again, I'll just piggyback off my work, and I'll just multiply x plus y times x plus y cubed to get x plus y to the fourth. And we multiply again using the double application of the distributive property. We've got x cubed, 3x squared, x cubed, I'm sorry, x times x cubed is x to the fourth. X times 3x squared is 3x cubed y. X times 3x y squared is 3x squared y squared. We just add 1 to each exponent, and then x y cubed. Then we multiply every term in this four-term expression by y, and we get x cubed y. Again, we keep it alphabetical, so we can see our like terms a little bit easier. And then 3xy squared, and then 3xy cubed, and then y to the fourth. So again, we have 8 multiplications, 2 by 4. So we'll do our 8 multiplications, and we combine our like terms. We've got x to the fourth. 3 plus 1 is 4x to the third y. 3 plus 3 is 6, x squared y to the second. And 1 plus 3 is 4x y to the third, and then 4. Now, we start to notice a pattern. Notice how my x starts out at the same as the exponent on the binomial, x to the fourth. And notice how the exponents go 4, 3, 2, 1, no x's. And my y's go no y's, 1y, y squared, y to the third, y to the fourth. So it looks like the x exponents are descending and the y exponents are descending. And we go back and look at the cube because it's the same thing. When we cube this, 3, 2, 1, no x's, no y's, 1y, 2 y's, 3 y's, or times y times y times y. And if you even go back to the squares, the same thing. Up here, x plus y squared, we start with x squared, x, no x's, no y's, y to the first, y to the second. So you start to see a pattern here. Let's try one more. And historically, this is probably what happened. We saw these patterns, and then mathematicians said, well, let's see what we can do here. Come up with some kind of theorem. So again, we're just going to piggyback off of this work. So I'll just say x plus y to the fifth is x plus y times x plus y to the fourth. And here we go. Multiply every term here by x. And again, our exponents and the x just increase by 1, so it becomes 5, 4, 3, 2, 1. And you can see that 5, 4, 3, 2, 1. And everything else is the same. Okay, the 4y, the 6y squared, the 4y cubed, and the y to the fourth. We just increase the exponents x by 1, then we multiply everything by y. So we have x to the fourth y, 4, x to the third, y to the second, 6x squared, y to the third, 4, x, y to the fourth, and then finally y times y to the fourth is y to the fifth. We add up our like terms, x to the fifth, 4 plus 1 is 5, x to the fourth y, 6 plus 4 is 10, x cubed y squared, another 6 plus, or 4 plus 6 is 10, x squared y to the third, 1 plus 4 is 5, x y to the fourth, and finally y to the fifth. This is over here. Okay, I think you can see that. And again, notice the same pattern. This is the fifth power. This is x to the fifth, fourth, third, second, first, x to the 0 power. X to the 0 power, remember, is 1. And no y's or y to the 0, which is like 1, then y to the first, y to the second, y to the third, y to the fourth, y to the fifth. So we see a pattern, and this pattern is going to lead to the binomial theorem. Okay? So now we're going to put this together and see if we can come up with some more interesting observations.